is I have the same exact words that you guys stared at before, but now they are arranged into two columns. There's the A column and the B column, all right? And it's not a random arrangement. There's a pattern. All the A's have one thing in common. All the B's have another thing in common. And I want you to look at your list and look at the columns and tell me, do you remember more from column A or from column B? So I remembered more from column A, or I remembered more from column B. And those are the two columns for you to stare at. It's different than what it was originally. They're sorted in a certain way. So look at your list and look at the columns. Okay, I got 14 answers. Maybe there's like 2 people left. I think it was 16 on the first vote. 4, 8, 12. Okay. Perfect. Okay, let's see. What do people think? Which column is better? Which one is the better column? So let's see what people said. And people said, 16 to 1. People said column B is the better column. It's out of the things you remembered, almost everybody, 16 people, remembered more things from column B. Does anybody notice the pattern? What was different about column B? They're missing letters. Yeah, all of the column B's are missing letters. In the column A, I told you the full words. In the column B, I was like, haha, I'm very sneaky. I'm going to leave out a letter, and you have to fill in the letter. Wait a minute. You guys remembered more from column A, right? No, wait, B. But in this one, I told you the full thing. I was like, here it is. Please remember it. And this one, I was like, let me just give them half. And you remembered that one more. When I first saw this, I thought it was like backwards. I was like, there must be some mistake with like the A's and the B's being reversed. Because very clearly, column B is the deficient column. It's the sucky column where things are broken. But somehow, you guys all remembered stuff from column B. Like you remembered more from the sucky column that is broken. But actually, if you think about it the right way, it makes sense. Does anyone have a guess of why column B is actually easier to remember than column A? Yeah.
We had to fill in the blanks, so we spent more time thinking about it.
You spent more time thinking about it. I think that's basically the idea. So like when cavemen were in the ancestral environment, there's like information everywhere, right? It's like, what do you pay attention to? And the way your brain decides what to pay attention to is like whatever you spend time thinking about, that's what it will remember. And that's why this column is sort of easier to remember. You just like have like how long did it take you to fill in lunch here? Like literally like a microsecond. And that amount of effort gives it a huge advantage over these ones that you just read and you don't think about. So what is the moral of the story? The fill in the blanks are actually really useful for learning because it makes your brain think about it, even for just 1 second, and that makes a huge difference in what you remember. So you guys, 16 to 1, that's pretty extreme. Normally it's like 90%, but 16 to 1 is quite impressive. Yeah, was there another comment over here?
Oh no, it just took us to like we're trying to figure out what the missing letter for the solve over this.
Yes, some of them are hard. So yeah, I guess, if the blank is so hard to fill in, like if it was all blanks, blank, 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 slash blank, 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 then of course you would not remember the word. So there needs to be sort of a balance between enough of a blank that you spend time thinking about it, but not enough blank that it's still useful. And that is why I do these like mathematized questions in class and stuff. So the idea is for it to be like column B. The class is supposed to be like column B, where you guys have to do a little bit of work, and hopefully that'll help you remember a little bit better. I don't know if you remember on Thursday, we talked about this trick in the last 2 minutes of class. This trick of thinking of the value you want to look at, the number of coin flips it takes, as depending on which state you're in. And instead of just telling you, which would be the column A approach, I had you think about it for a little bit. We're going to keep doing it today. But that's sort of this exercise is to show you the way I sort of think about learning and why we do all these blanks in class. Plus we're in person and we're having fun, so it's more fun to have like some interaction stuff. If you go online and you watch a video, right, or read a textbook, it's just like they just give you all the information. I want the class to be more like this, where we work together and fill in some blanks. Any questions or comments about the learning activity? All right, some people might have done that already. I do this in a lot of my classes. But here's the actual first question today about what we're doing about. And it's, having to do with the coin flips. So you remember last time we said, how many coin flips until the first heads? And now we're going to answer the question, how many coin flips, not until the first heads, we're going to do how many coin flips until the first heads. So you need 2 heads in a row. How long will it take? And we're going to do this by setting up a Markov chain. And the Markov chain is going to have 3 states. So this is our first Markov chain other than snakes and ladders. In snakes and ladders, we have like 9 states. This one only has 3 states. State 0, state 1, and state 2. And the states are how much progress you have. So state 0 is no progress or 0 progress. State 1 is 1 head done and 1 head to go. So if you're flipping coins, you got tails, 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 that's no progress. But then when you get your first heads, you're like, yay, we're in state 1, we're halfway to heads, heads. And then state 2 is 2 heads in a row. And then you're done. Once you get to state 2, you have gotten the heads, heads, and you're done. So the question is, how long does it take to get to state 2? It's a little bit like in snakes and ladders we said, how long does it take to get to state 9, that final square? And the first question I want you guys to do is to fill in the blanks for the matrix. So here's that P matrix. I filled in some of them, but some of them are not filled in. And you guys should fill in the rest. There's 5 boxes to fill in of this P. You have to remember the interpretation of the rows and the columns of P. You have to think about these states and how coin flips work. By the way, they're fair coin flips, so 50-50 chance for heads and tails. But I'll give you guys a couple minutes to fill this in. Okay, and hopefully you'll remember it. Okay, let's do, say, 2 minutes. Yeah.
Is Markov transition matrix the same thing as the probability transition matrix?
Yes, yeah, it's the same thing. Okay, there's like 20 seconds left. Put in your guesses. If we need to revote, we'll do a revote, but I want to see how people are doing so far. I know not everyone has answered yet. Okay, it's dinging, so put in your final guesses here before I press the reveal button. And let's see, what do people say? Okay, reveal counts. Okay, so some of them are tricky, some of them are harder, and some of them are easier. Let's start with, I think the weirdest one is this bottom corner. Let's see what people said for the bottom corner. And for the bottom corner, 16-1, people said 1. 1 is the right answer in the bottom corner. So this bottom corner, it represents the state 2 transition, and you know it's state 2 because it's in the number 2 row. It's a little confusing if you're not used to starting at 0. The number 2 row is the 3rd row because the 0th row is the one at the top. So that's the number 2 row, that's state 2. And if you're in state 2, you're done. You just stay there forever. So just like in snakes and ladders, that is a 1. So very good. Almost everyone got that. The other thing that this thing can be helpful for is to remember there's something special about sums in these matrices. And the thing that's special is the sum of every row has to be 1. So if you have 0, 0, 1, that adds up to 1. It's saying there's a 100% chance starting from state 2 to go somewhere. In this case, it's always going to state 2. But the sums always have to be 1. And you kind of look at it row by row. So that's a helpful hint. Let's see how you guys did on the other ones. Row, the first row, the 0th row, the top row. All right, 10 people said 0.5. Some people said 1. Somebody said 0.51, which I don't know how that's going to come up, but okay. What about for this one? A little bit mixed also. Some people said 0. Some people said 0.5. What about these other ones? 0, 0.5, and 0, 0.5. Okay, so a little bit all over the place. I will tell you for sure, the majority is wrong in at least one of these squares. So if you're kind of trying to like go with the majority is wrong somewhere. But maybe now with the hints I gave, so think of them row by row. Remember that the sum of every row is equal to 1, and each row is like, where do you go from that state, right? So state 2 is where do you go from state 2. This row is where you go from state 1. This row is where you go from state 0. We're going to have a revote, and let's see if you guys can get it this time. Feel free to chat with your neighbors and try to work on it together. Say what you put on the first round, see if they put the same thing. If you guys disagree, maybe one of you guys is right. Okay, I'm going to revote it, and we will reconvene in a couple minutes. All right, see you soon. Okay. Okay, it's open again. Even if you want to stay with the same answers, you have to type your answer in again. And we'll see what you guys said in a minute and a half. All right, like 20 seconds left. Put in your final guesses on what you think it is. All right. Okay, you guys are getting very well trained for the dinging. As soon as it starts dinging, the last few people immediately jump in. Okay, this is great. What did people say this time? Okay, so hopefully everybody still got this. Yay, okay, 17 people. First, the top row is state 0, so you have no progress. If you have no progress, what could happen? And 13 people said 0.5 for the top right entry, or the top left entry, and the top middle entry, 14 people said 0.5, and those are both correct. So it is 0.5, 0.5 in the top, and that says if you have no progress, then on the next coin flip, then you will either still have no progress, or you will move up to 1 progress. And you move to no progress again if you flip a tails. If you have no progress and you flip a heads, then you move to 1 heads out of 2. So you either go to state 0 or state 1 50% of the time. Let's draw this out. Actually, this is one way, a nice way to represent some Markov chains that we haven't done yet, which is to draw them as a little graph. So I'm going to draw it like this. And I'm going to draw no progress, which is like a big blob over here. That's the state S equals 0, state 0. And then there's 1 progress, or like 1 progress, which is S equals 1. And you can kind of draw these connections as little arrows of where you move to. And half the time you move this way, and half the time you stay where you are, which you draw as like a little loop. Whoop, probability equals a half. And this is if you flip heads, then you move up on your progress. But if you flip tails, then you stay where you are with no progress. And so this is one new way of thinking of a Markov chain. You think of a state as a vertex, and one row gives you these arrows coming out of it. You could also, if you want to be really pedantic, you could say this is to progress, aka done, which is the state s equals 2. You could also draw a third arrow like this and say probability 0, right? And that's why the top row is 1 half, 1 half, 0. It's the probabilities to move to state 0, 1, and 2. But normally we don't draw this last one, so you just leave it out. If it's probability 0, just leave it out. So it's a 0 entry in the matrix, but we don't even draw it on the thing. So okay, they're very good. So people got that one right. A half, 0. What about the next one? The next one's trickier. What is it? Woohoo! 9 people said 0. And for this one, very close to a 50-50 split between a half and 0. The majority answer was 0.5, and this is one of those situations where the majority in the middle row got it wrong. So the correct answer is 0. It's a half, 0, 1 half. Let's draw it out and see what it looks like. So if you have one progress, that is a sequence. So that's some sequence that ends with a heads. Okay? And on the next coin flip, what's going to happen? If you have a sequence with a heads, well, 2 things can happen when you flip a coin. Either it's going to come up heads or it's going to come up tails. If it comes up heads, 2 things can happen. You can either become heads and then you tack on another heads, or another thing that could happen is we could tack on a tails. Heads and tails. And here's the thing. So if you flip a heads, then you move here. That's probability equals 1 half, and you're done. You flip heads. But in the other universe where you flip a tails, what is your progress now? You're at a sequence that ends in a tails. How much progress are you making towards having a sequence of heads, heads? Well, you have no progress. You go back this way. So this has probability also a half. And that's because now your sequence ends with a tails. Having one heads on its own over here is not helpful. You need 2 heads in a row. So this tails effectively restarts you. You're back to square 1, or square 0 actually. You have no progress, you gotta start over. As soon as the tails comes up, now you're playing as if you had just started again. So you go back this way, and because this is the 0th entry is a half, the last entry is a half, and you'll notice there's no probability to stay where you are. This is probability equals 0. So the vector that we're gonna read off in this row is a half, 0, a half, and that is what is written here. Okay, a half, 0, a half. And yeah, it's always exciting when the majority gets it wrong. It means we have something to learn. And yeah, I guess people were backwards on where the zeros and the half goes. Any questions or comments about that now that I've explained it? Okay, so this is what it looks like as a thing. As a graph, that's what it looks like. And as a matrix, it is this matrix, right? 1 half, 1 half, 0, 1 half, 0, 1 half, and 0, 0, 1. Let's add that to our picture, right? If you're done, you just stay here forever. That's how we think of these terminal states where the game is sort of over, but we just stay there forever so that we can run it for some amount of time. Okay, we're going to answer the question now. How many coin flips? How many coin flips does it take to flip heads, heads until we flip heads, heads? So, you're just saying how many coin flips is it going to take? Does anyone have a guess? We can lock in I always make my son do this. What's your hypothesis on what the answer will be? Just quick we're going to calculate it, but off the top of your head, yeah. 5. Great guess. Anyone have anything else? Yeah. 4. Yeah, I think 4 is the intuitive one, because it's like you gotta get heads, heads twice. If you flip, it's like a 1 in 4 chance of flipping in 2 coin flips. It'll be a 1 in 4 chance you get heads, heads right away. So it's like we do that 1 over p thing, right? If you have So 1 over p would be like 4. So these are great, good guesses. Let's see if they're right. Good guesses. And there's no reason it has to be an integer, right? It could be like 4.2, right? Because it's the average number. So if it takes 4 sometimes, it takes 5 sometimes, the average could be any old number. Let's see what it is. Okay. And how are we going to do it? Again, the secret is we're going to look at this random variable, n heads heads, right? The number of coin flips until heads heads. And this is the secret we stumbled upon at the very end of the class on Thursday. If you try to do n heads heads on its own, it's quite hard. But if you make a generalized version of the problem, you don't do just n heads heads. You do n heads 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 as a function of s is the number of coin flips until heads heads starting from state s. So you look at the Markov chain that we just did. Yeah, let me fix this n is looking a little weird. And you think of it, depending on where you start, there's a different number of coin flips until heads heads first appears. So depending on if you have 0 progress, 1 progress, or 2 progress, let's figure out that whole thing. And the reason it's nice to do this generalized thing is it's gonna depend on itself. So the number of coin flips it takes until heads heads when s equals 0 and s equals 1 will depend on each other. And we're going to get a system of equations, and we can solve it. If you just try to do it on its own, like this, then you don't have a system. So there's no system of equations. You just have one. You just have one of the guys. So this looks harder because it's more work, but it's actually smarter because you have the whole system all together, and then you can use like linear algebra to solve it. So that's what we're going to do. And so let's figure it out. The first thing we're going to do is write down some of the equations that we know. I'm going to do an easy one first. What is n heads heads of 2? N heads heads of 2. So let me write s equals 2 so we can be really clear with that. That's like the number of coin flips it takes until you get heads heads, but you already got heads heads. Well, that should be 0. So I think any reasonable definition is 0. You are already done. Already done. So if you're watching this sort of sequence of coin flips evolve, and you're like, I've already flipped heads heads, how many more coin flips do I need? You need 0 more. It's very reasonable to have this one. So that's very nice. That leaves us with 2 things that we gotta figure out. N heads heads when s equals 1, and n heads heads when s equals 0. And these will be random. So I'm writing capital N because it's a random variable. So you can't say what it is exactly, but what you can do is kind of give it a distribution. So I'm gonna say, what is it? It's going to be sometimes one thing, sometimes another thing. And then we're going to take the average values to get some honest equations with no weirdness. This is a little bit like what we did for a geometric random variable that was 1 coin last class. And it's going to do one thing with probability 1/2, and it's going to do one thing with probability 1/2, depending on if you flip a heads or a tails on the next coin flip. And in fact, the thing it's going to do is exactly something to do with these kinds of transitions that we started the class with. So if you are at s equals 0, then what happens? Well, half the time you stay at 0, and half the time you move up to 1 progress. So half the time it's going to be another copy of n heads heads of s equals 0, and half the time it's going to be another copy of n heads heads when s equals 1. And here, so tilde means an independent copy. They'll say x tilde of x, just like we did last class. So I don't know what this is, but I can sort of relate it to itself. And in fact, in this case, it's related to when s equals 1 and s equals 0. There is one thing that I left out that I need to include for this to be correct. Does anyone know what is missing from my little equals sign over here? Okay, I left a little space right here. You can squeeze something in right here. Yeah.
It'd be like a 1 plus because you felt the phone.
It's exactly, it's a 1 plus. So, right. So if you flip the coin and you get a tails, and you go down to this situation where you were already in, you've used up 1 coin flip. So it's going to take you 1 extra coin flip than what it would have taken you right? So, whatever the first coin flip is, you got to count that somewhere. So don't forget this 1 plus. This represents the coin flip happening now. Very good. And that is exactly the same as our geometric random variable from before, right? You flip now, you got to count that 1 plus, and then you can get a system of equations. Because it's a 1 plus in both universes, you could also pull it out, but let's leave it like that for now. Okay. Questions or comments about the s equals 0 case? All right, let's do the s equals 1 case. And again, we're just going to read off from our little picture, or equally well, we could read it off from the matrix. What is going to happen when you have 1 progress? Well, half the time you're going to move down. That's exactly the same as the sort of situation where you move like that. That'll be this thing on the bottom. So it's going to be sort of a direct copy of this guy. It'll be 1 plus this n tildes head of s equals 0, right? Half the time you move down to state 0, and how long do you have to wait until the heads comes up? Well, 1 plus however long it takes from there, right? So that's an exact copy of this situation. You move to state 0, you got to wait as long as you got to wait. The other one is even better news for us. So if you're at 1 coin flip out of 2, and you flip a heads, then you're just done. How long does it take? Well, then it's just 1 plus nothing. So it's just 1. So you could write just 1. That's perfectly correct. You could also, if you want to make the pattern, you could write 1 plus n tildes heads of s equals 2, right? Right? Because you move up to state 2, and we know that that one is 0. So it's 1 plus 0. It's going to be 1. In any case, there it is. Okay. Questions or comments about how that got filled in? This is exactly the same thing as the Markov transition matrix, right? Those are the rules that tell you where you move. And then I've added on this logic of what happens if you're in this state. Well, you have to wait 1 coin flip. That's the 1 pluses are the only kind of extra thing. All right, now we're going to take the average, and we're going to turn these equations, which are like equations for random variables. When you take the average, they will turn into honest equations for numbers, right? So take the average, take average. That is this E operator. So it's like you're taking this E operator, which eats random variables and outputs their average value. You're applying that to the left-hand side and the right-hand side. On the left-hand side, we get some nice equations. So the expected value, and we're going to write it like this. N heads given s equals 0. And let me also use this notation S0, right? So the Markov chain is a sequence of random variables. If you start, that's where you are at time 0, at state 0, or at state 2, or at state 1. I guess I want to do it starting at state 2. And this at state 1 will be the next 2 lines to keep the order the same. So this is how I would write this thing with expected values. So starting at time 0, at either state 1 or 2 or 3, or at site 0 or 1 or 2. And this one is 0, because the random variable is always 0, so its average is 0. And now we take these equations and we unfold them into numbers. If you're half the time you're something and half the time you're something else, then on average, we get an equation which is half the time a half times something plus a half times something else. And the something else's are 1 plus, and now it's the average value. The average, let me do this in a different color, so try to highlight what's going on here. The expected value of n heads given s equals from 0, and half the time it's 1 plus e of n heads given s equals 2. So half the time you move to state 0, half the time you move to state 1, you always add on a 1 plus from this state. So this is a sort of a folded down average version of this equation over here. Maybe I'll try to zoom out so you can see everything at once. So we've sort of taken that thing and collapsed it down by taking the average. Okay, now we're going to do it again for the other one. And this one is very similar, but a little different. 1 plus the expected value. You move to state 0, that part's the same, or you move to state 1. Okay. Fantastic. So we got a nice sequence of equations. You got three equations. Technically, I guess there's three unknowns, right? The three unknowns are on the left-hand side, and there's three equations. You should be able to solve this. It's actually really two equations and two unknowns because the top equation is quite simple. But basically, the point I'm trying to make is that the Markov chain rules, they tell you what's going on the right-hand side in terms of what's on the left-hand side. It's a weird combination involving all those probabilities, and we can solve it. So let's do it. So the first thing I'm going to do is I'm going to simplify this one. This one is 0, right? If you go to state 2, you're done. So that's a 0. So we can rehash these equations and simplify them a bit. Let's see. So there's a half over here. And there's another half over here. So the first equation, you know what? It's quite annoying to write all these things out all the time. Why don't we give it a name? Let's call it V. Let's call it V of S. That'll be the expected value of n heads given S0 equals S. And what do our two equations say in terms of V? They say V of 1, that's this line, it's equal to a half plus a half V of 0 plus a half plus 0, which is 1 plus a half V of 0. That's that equation simplified with ordinary algebra. The last line over here says something about V of 0. And V of 0, it's, again, you have a half plus a half, so a half plus a half. And you get V of 0 with a half plus 1/2 V of 1. So this is the equation 1 plus 1/2 V of 0 plus 1/2 V of 1. Okay, great. So two equations with two unknowns, we should be able to solve it. And here's the beauty of algebra. You can move this to the left-hand side, right? So what you get is a half V of 0 equals 1 plus 1/2 V of 1. In other words, V of 0 is 2 plus V of 1. Okay, great. So whatever it is if you're at state 1, V of 0 is that plus 2. On the other hand, this equation says V of 1, let's do this in blue. V of 1 is 1 plus 1/2 V of 0. And now if we take this equation and plug it in, we get 1 plus 1/2 times 2 plus V of 1, which is also known as 1 plus 1 plus 1/2 V of 1. Okay, so V of 1 equals 1 plus 1 plus 1/2 V of 1. So V of 1, 1/2 V of 1 equals 2 implies V of 1 equals 4. V of 1 equals 4. And if V of 1 equals 4, then V of 0 is 2 plus 4, which is 6. So we've solved the whole system. We got these equations in terms of themselves. In this case, the answer was, starting at state 1, it's going to take you 4 flips on average to get to the end. Starting from state 0, it's going to take you 6 flips. And that is a solution to the equations. So what is the answer to the question we're looking for? How many coin flips is it going to take? It's not 4 or 5. The answer was 6. So you guys were close, but not right. Okay, so it takes 6 flips. Yeah.
Is 5 the answer for when you do heads, tails?
No, it's not. 4 is the answer when you do heads, tails.
Okay.
Yes, this is great. A great question. Yeah. So if you have a different sequence, instead of heads, and you go for heads, tails, it's going to be 4. This thing will be slightly different. And there's a clever trick to figure it out in general. I'll post a video. There's also a tab on CourseLink called Related Videos, so I'll post it there to do it in general. But what we've learned is sort of like hands-on way to do it, and it takes 6 flips on average. Okay. The main thing we're trying to do is figure out how this system of equations works and sort of like get an intuition of how it works. And so the idea is you're looking at this thing and you're like, how long does it take from each of these states? It all depends on each other. That's the main idea that we want to take away here. Any questions or comments about that idea? Okay, we're going to do it in general now, right? So this is like a whole kind of by hand. Remember, like our very first class, we did stuff by hand in spreadsheets, and then we're like, this is crazy. Let's do some real linear algebra. Same thing in general today. So we did the sort of like basic version to with 2 states, like V0 and V1, to sort of get the idea of thinking of each state as where you're going and like how they depend on each other. And now we're going to learn the general version. And the general version of this equation is called the Bellman equation. So we're going to now, what we just did is a version of the Bellman equation. So Bellman was some guy, and he came up with this equation. And actually, the Bellman equation is a little bit more complicated than what we're going to do today. So what we're doing today is what I call the baby Bellman equation. And we're going to learn the real Bellman equation a little bit later. But the Bellman equation sort of tells you how to learn these values v. And we're going to do it for something I call a Markov reward process. Markov reward. All right. And this reward part is new. So far we've done just a regular Markov process or a Markov chain. So we're going to introduce these rewards. And this is all in chapter 3 of the textbook, if you also want to read the definitions there. And we're just going to add on one extra detail to our definition so far. So far we have these states. And what is a Markov chain? It's a sequence of these random variables. You got S0, S1, S2, and S3. And we're going to tack on, and we're going to sort of think of as you move from state 0 to state 1, and as you move from state 1 to state 2, you are picking up a reward. So en route, you get these rewards, and those are a sequence of new random variables called R. So the S's are states. ST is in the state space S, right, of all possible states. A state, random variable. That's what we've been doing so far. And now we have a new thing, which is a reward random variable. And that's what we're going to use the letter capital R for the rewards. And you're going to get these R's sort of in between the states. As you move from one state to the other state, you see this reward. And the reward, importantly, it is not a state random variable. It is an honest-to-goodness real number. So R is going to be a real number, the amount of reward. And it could be a random variable. But it is the reward, the amount of variable, the amount of reward. Okay, reward. And if you remember from our first class, the rewards are how we sort of tell the system what is good and bad, right? Good things should have high reward, bad things should have low reward or even negative reward. And the systems we're going to come up with are going to sort of like maximize the reward. Of course, we don't have actions yet, so that'll come soon. For now, we just have states and rewards. There is one thing I have left off here, which is I said the sequences are a sequence of rewards, right? The reward you get, the first, the second reward, the third reward, and so on. They come in between the things. You have to make a choice. Are you going to call this one, is it going to be R0 or is it going to be called R1? Right? It happens in between 0 and 1. So both R0 and R1 would be totally valid names for this guy. Who thinks we should call it R0, right? The reward you get at 0. Who thinks we should call it R1, the reward you get going into state 1? Okay, nobody voted for that one. Who doesn't care? It's like, just pick one, man. Okay, nobody doesn't care. 0.5, yeah, that'd be a great name. So we're gonna go with R1, and that's because that's what this textbook does, okay? So unfortunately, I don't wanna change the notation too much. I kind of agree with you guys, it should be R0. 0.5 would be genius. Yeah, I think, well, anyway, so this is what we're going with. I don't know however you want to square it into your brain. The R1 is the reward you get leaving state 0 and going into state 1. And I will give you a perfectly good example of these things. The example we started the class with is an example of these. So example. In the heads Markov chain that we started the class with. So how many, the reward, I'm going to put reward in quotes because it doesn't really have an interpretation of reward. It's just some real number. Is, what is it? RT. It's equal to either 1, or 0. And this is if st minus 1 equals 0. If st minus 1 equals 1, and 0 if st minus 1 equals 2. So it's either 1, or 0, and it sort of represents how many extra coin flips you have to keep flipping to keep going. And it looks at the state before, right? So RT looks at st minus 1, the state before you were there, And it's just saying, it's kind of like labeling, if you like this picture, it's kind of like labeling the arrows on this picture with little rewards. And we're saying, look, the reward you have to get is +1 over here. The reward is +1. This reward is a +1. This reward is a +1. This reward is a +1. And this reward is 0. And the reward here is just counting how many coins. So it's a little bit silly to call it a reward. It's counting how many coins are being flipped until we finish the game. And here it only depends on where you left from, right? In general, it could depend on where you left from and where you went to, but in this specific problem, it depends only on the state you are leaving, and it's always either 1 or 0. And the interpretation is, here is that reward is just number of coins, right? Reward is the number of coins flipped until heads is reached. Or I should say, I should be careful. The total reward will be this. Okay. So the reward is like some number that measures something we care about. As we go in the course, it really will be like a reward, like good or bad. For this problem, it's like how many coins. Is that good or bad? I guess it's your choice on the interpretation. I will say very often, you'll see a reward of like this, like 1s and 0s, or sometimes negative 1s and 0s, and that will count for a length of time. So I think one of the examples I gave in the very first class was like a Roomba robot trying to find its way to a charger. Very common to give it a reward of -1 at all the states except for the state where it's docked. And then it will try to sort of like find its way as quickly as possible, right? Another situation, maybe you have like a balancing robot. So you have like a little cart and you want to balance a pole on top of it. You give it a reward of +1 whenever the pole is upright, and a reward of 0 if the pole falls over, and then it will try to maximize the total reward. It'll try to keep the pole upright for as long as possible. So this kind of thing with 1s and 0s is actually pretty common. Questions or comments about what is a reward? Okay. The reward, like the states, must satisfy a Markov property. Otherwise, it is not a Markov reward process. And so it must satisfy this Markov property. It must satisfy a Markov property. And the Markov property, again, Markov was just some Russian mathematician. The Markov property is just telling you that if you know the state, then everything that happened in the past does not matter, right? So just like in snakes and ladders, how you get to a certain square, once you're at the certain square, how you got there doesn't matter anymore. It needs to be the same thing for the rewards. And so, informally, it just says rewards depend only on ST. Let's say RT, the reward RT, depends only on ST, not how we got there. That's a nice informal definition. And if you want the math version is an equation about probabilities. It says the probability that RT equals some value R, let's also include ST plus 1 equals some value S prime. Oh, I guess this is SRT plus 1, okay. Okay, look, I'm off by 1, right? This is a stupid 0, 1 thing. RT plus 1 depends only on ST. So if you want to know what's the chance of having a reward R and going to position S prime, given, what are you given? If you're given the position ST equals S and a bunch of other information like ST minus 1 equals S, I'll call this old, ... So you're given a whole bunch of useless stuff. Let me color code this a little bit more. Let's make this one nice orange color. ST equals S. So if someone says like, I want to know what's the chance of the reward being R, given all this information, where I was, and all this information about the past, well, the stuff about the past is useless. It doesn't do anything. You might as well delete it. So this will be the same exact equation with that stuff deleted. ST plus 1 equals S prime, given, and the only thing that sticks around is ST equals S. Everything else from the past is useless. You might as well delete it. It doesn't affect the probability of the reward. And this is just saying if you know you're at state S, that's the only thing that matters. How you got there doesn't matter. Everything, all the information is contained in the state S. Okay, that's the reward, or the Markov property for the reward. Any questions about this one? It's a bit of a technical statement. Okay, Let's make sure, did that happen in our example? It worked in our example because, right, this is always 1 or 0. It just depends on the state you were leaving, how you got there, how long you've been waiting for coin flips does not affect this reward. So very good. Okay. How am I doing tonight? Okay. I'm going to do something a little informal here, and we're going to expand on this later, but I think it's worth pointing out now, which is that rewards can be divided into 2 sort of rewards. There's 2 types, very roughly speaking. There's something I call ongoing rewards. Ongoing rewards. And these are rewards you can get multiple times. You can get over and over again. And in the example that I'm thinking of, right, this example with the coin flips, let's see. Okay, where is it? Here it is. Like you can hit this reward a bunch of times. You go like in a loop. You're getting all sorts of rewards while you're waiting for the coins to go. So these are ongoing rewards. And in some problems, there is a different thing that you get one time on one time only, and I call these a terminal reward. So the example you've seen so far is an ongoing reward, and there's also something called a terminal reward. We will have more about these in a future class, but I wanted to sort of give you a heads up about this kind of thing now. Yeah?
What are the, well, I guess I was going to say, what are the reward of restricted state 2 can only be terminals from, say, one of the that's wrong. So.
Yeah, okay, so this is very informal right now. Like, it doesn't have an actual definition. I just want to give you a heads up so you can, like, think about things in your brain the right way. So the rewards we've done so far with this, like, +1, you should think of as an ongoing reward because you can, like, sort of hit the state over and over again and pick up a lot of rewards. And I'm going to give you an example now. It's an example I gave in the first class, which is in chess or other board games. You can think of the reward of a state is, what is the reward of a state? It's equal to +1 if state equals white 1. So the game's over. Like you're looking at the board and you're like, the black king is checkmated, white has won the game. That's a reward of +1. It's a reward of 0 if state equals tie. And it's a reward of -1 if state equals black 1. Okay, and the point is that this reward is only at the very end of the game, right? And that's what makes this a terminal reward. This is an example of a terminal reward. And it has a kind of a different flavor than the ongoing rewards that we're doing in our problem. So they kind of like have 2 different ways of thinking about it. Technically, you can think of this as like the state. You can make the Markov chain all the possible games of chess plus 1 state that is like the game is over. And then you can say, when you transition from a state where white won into the game over state, then you get your +1. So like on a mathematical level, this is exactly the same as the reward. Like I could have just skipped all this and said, there's only one type of reward. It's a sequence of random variables, blah, blah, blah. But these sort of have 2 very different ways of in your brain. And we're going to see that when you code it, it's convenient to think of them slightly differently. So I'm telling you now, we're going to have more about this later. But that's the gist of it. You can get a reward right at the end of the game, or you can get rewards like throughout the game. You can set it up either way. Yeah, okay. Questions? Okay. So the thing we're going to try to do is come up with an equation now for these rewards. And the equation we're going to get is going to be exactly the equations we had over here, but it's going to be written in a nice vector valued way. It's going to be with vectors and with the probability matrix capital P. And the equation we're going to get is for the value function. So the value function. What is the value function? And maybe more technically, it should be like the value function, the reward value function or something. But everybody calls this the value function. And it is a function v of s. And it is exactly what we had before. V of s, it's going to be the average of the total reward from state s. So here I'm going to write total reward. And it's going to be starting from state s. So just like we saw in the how long you wait. If the reward is coin flips, then it's the expected value of the number of coin flips it takes until you reach heads heads. The total reward in general, you can write it as a big sum. So you could write R1 plus R2 plus R3 plus dot dot dot. This total reward has a name, which is kind of confusing. This thing is called the return. The return. I'm gonna sometimes try to use the word total to sort of distinguish it. But very technically speaking, if you open the textbook and you're like, what is a return? A return is the total, the sum of the rewards starting at some point. And in fact, the textbook defines this with a random variable. They call it GT, which is the total return after time t. Return after time t. And it's this infinite sum. Okay, let me make sure I'm not off by one in my R's and T's. Yeah, okay, here it is. So it's R t plus 1 plus R t plus 2 plus R t plus 3 plus R t plus 4 plus dot dot dot. So you add up the rewards forever, starting at time t. And so the value function, what is it? You could equally well write it, this whole thing over here, this is equal to G0. You could say it's the expected value of G0 starting from state S. Okay, so that's a bunch of definitions, right? The value function, the total return, the rewards. Any questions or comments? That's all good? Let me throw one more definition at you, which is something called a discount factor. This is the future discount factor. And if you've taken like an economics class, you might be familiar with this concept of you want to think of like money you have in the future as less valuable than money you have now. Because money you have now, you can like invest it and have like even more money in the future. So you're going to have this factor gamma, and gamma is some number in 0, 1, and it is like how much you would discount a future dollar so that it's equal to $1 today. So for example, if it's a half, then you're saying, I would rather have $1 today than it's exactly the same value as having $2 tomorrow. This is like if you live in a country with like a lot of inflation or something. You'd rather have $1 today than $2 tomorrow, then gamma would be a half. And you can put this in your definition of the return. So that's called the discounted return. And what you do is you put a factor of gamma and a factor of gamma squared here and gamma cubed. In this course, very often gamma will be 1. So 1 is allowed as a thing. But just to give you the full definition, there's a gamma, and that is the thing. This also lets you, helps with the convergence. So sometimes you'll have GT as an infinite sum. If you start putting in factors of gamma, it'll tamp it down and it'll converge more nicely. So that's a nice feature. Yeah.
0 also allowed?
0 is allowed. If you put in 0, then I guess you're saying like, I don't care at all what happens tomorrow. I only care about what happens today. So you're going to get some wonky behavior at 0. So I don't know. You don't put in 0. you can if you want, I guess, but it'll be weird. So yeah, let's exclude 0. I don't remember what the textbook does. You guys can check. Okay. Questions, comments? Okay, so now we have all the setup. We're going to do exactly what we did at the beginning of the class with this value function v of s. You saw before we got a nice system of equations for v of s sort of by hand. We're going to try to do it more systematically. And if we think of v of s as a vector, right? So v of s really is like a vector, right? It's v of state 0, v of state 1, v of state 2, dot, 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 all the way to v of state n. And if you think about it as a vector, you can get a nice equation for it that is equivalent to the equation that we did over here, right? Over here it was a big mess. We're going to try to clean it up and get it really nice. Okay, let's do it. So here is what we're going to do. We're going to write down, so this is the derivation of the baby Bellman equation. And we're going to start with what is v of s. It's the expected value, remember, of g0. Actually, yeah, let me write out let's write out g0. Okay, g0, given s0 equals lowercase s. Okay, great. So here is the whole trick in a nutshell, is that g0 is actually related to g1. And so here is the claim, is that if you go back up to the definition, here is we're going to use G0 equals the reward you get now plus gamma times all the returns in the future. That's the equation we're going to use. And the reason this works is if you expand out what is G1, right? This is R0 plus gamma. G1 is R1 plus gamma R2 plus gamma squared R3 plus dot, dot, dot. So the return after time 1, if you discount it by a factor of gamma and you add it onto R0, that's the total return from G0. So it's just a kind of a manipulation of the infinite sums. Yeah?
In the above, you have G of t be starting from R2 plus 1, so it shouldn't be R2.
Oh yeah, I'm probably off by 1 somewhere. Okay, let me see. Yeah, okay, great. Thank you very much. This is actually an R1, and this should be R2. Yeah, this is 100% just the convention of do you count your rewards? Do you label it as a 0 or a 1 for the first one? And you should label it as a 1. So the first reward is R1. Okay, thank you, very nice. So I don't know, this is how the textbook does it, so that's how we're gonna do it too. Okay, this is a super important concept, right? It's saying the total rewards you get will be the rewards you get now plus the rewards you get later. Sounds like a really simple idea, but it's actually it's very powerful. Think of now plus later, right? And what you want to do is maximize the sum of now plus later. All right, that's what we want. So let's put that into our equation. So it's the rewards we get now, R1. And let me even factor things out. So it's S0 equals S. And then I'm going to do plus gamma times the expected value of G1 in purple. G1 of S0 equals S. And this is V of S. So basically, the value of our state, like the total value on average we're going to get from our state, is what we get now on average plus what we're going to get after we move to the next state, right? What we're going to get in the future, okay? And this vector over here, this thing has a name. This is just some vector. It's the reward you get from state S. This is the average reward from state S. Some people call this the reward average vector or something. Reward from state S. In the textbook, they call this R of S. R of S. And in our example, this was a very nice vector, right? If you think of this as a vector, it was the vector 1, 1, 0 in our example. So just how much reward are you getting at any given state? On average. That's just some vector. All right. This one is the exciting one. In this one, we have sort of moved time forward by 1. We have G of 1, but we're given S0. Okay? And we actually did this kind of equation last class. If you want to know the expected value of something in the future, given what we have now, that was the Kolmogorov backwards equation. So it's going to turn out that this is going to be equal to, very simply, it's the matrix P times the vector V. It's P times V. That's what we're going to find out. Let me expand it out to show you why, in case that wasn't 100% clear. So all you got to do is write, given S0 equals S, why don't we say what happens at time 1, right? And at time 1, a bunch of things could happen, right? So this expected value, if you want to know what it is, you write it as the sum over all possible states S prime, and you say, what happens at state S prime? So instead of being given that S0 equals S, why don't we say we're given S1 equals S prime and S0 equals S? So this is the law of total probability again, conditioning on what's going to happen after one step. And you have to sum over all the possible things that could happen, and you have to multiply by their probabilities. And you multiply by the probability that S1 equals S prime given S0 equals S. So this is a common trick in probability. You want to figure out an average, you split it up into a bunch of pieces, you multiply by the probability of each piece, and add them up. Okay. And now we use the Markov property. So by the Markov property, if you know that S1 is S prime, and you know that S0 equals S, then you might as well forget about this. So you can forget this. forget. Okay. And the reason you can forget it is if you know that the state at time 1 you're at state S prime, then it doesn't matter where you came from, right? Once you are at state S prime, what happened, how you got there, the history of the steps you took to get to S1, all of that doesn't matter. And this is the Markov property. Okay. And specifically, it's the Markov property for the rewards, right? G1 is made of all the rewards. So if all the future rewards can forget where you came from, then this is an okay operation. And if you do that, what do you have? You have the expected value of G1 given S1, right? But G1 given S1 is going to be the same as G0 given S0. It's a Markov chain. It doesn't matter what time it is. It only matters where you are. So this whole sum, this will be the sum of S prime in S, and it's going to be the value function V of S prime. That is the first thing. V of S prime, because we're at state S prime and we're looking at the rewards, the total return in the future. And then you multiply this P, this is exactly the probability transition matrix. So this is what we called P of S prime. P of S prime. The S prime entry of our probability matrix. Okay, and if you're doing a sum like this, the sum over all the S prime, V of S prime times P S prime, that's exactly a matrix vector multiplication. So this is equal to P times the vector V, and then please take the S entry. Okay. So what is, in total, what do we have here? We have V of S is equal to R of S plus PV, take the S entry. So as vectors, you could say, as vectors, what is it? It's V equals R plus PV. That is the whole equation as vectors. Very nice. And here V is the value function vector. Value function as a vector. R is the average reward from state S as a vector. And P is the transition matrix. Okay. Okay, and you can see it involves the matrix vector multiplication with V on the right. So if we're thinking of these things as column vectors, maybe I should write that. These are both column vectors because they are like values. And we think of these values as column vectors, and we do the matrix multiplication like this, then it is perfectly correct. Okay, this equation is the baby Bellman equation. Later in the course, we're going to get an extra fancy version of it, a full Bellman equation that's going to have actions as well. But we're going to start with this one now. Any questions or comments? Yeah. What happened to the what? Oh, the gamma. Yeah, I forgot the gamma. Yes, I should put gamma back in. Very good. There should be gamma. Okay. Yes, it's because I'm thinking of gamma equals 1. Let's write that down. Gamma in 0, 1 is the future discount factor. Okay. So that's the Bellman equation, or the baby Bellman equation. Let's do our example again. In our coin flip example, what is the equation? This is what we already did. In that thing, R was equal to the vector 1, 1, 0. Right? So from state 0 or from state 1, it's a 1. From state 2, it's a 0. This is the rewards. And in fact, it's not just the average. In this case, it's like non-random. Right? The amount of reward you get is this. So the equation says, and we had P, right? P was this matrix. It was 1 half, 1 half, 0, 1 half, 0, 1 half, 0, 0, 1. This was the heads example. And so in that situation, what you get is the equation V equals 1, 1, 0 plus 1 half, 1 half, 0, 1 half, 0, 1 half, 0, 0, 1 times V. And so this is an equation for an unknown vector V. And if you solve it, you are supposed to get the solution we got, which is V of 0 equals 6, V of 1 equals 4, and V of 2 equals 0. All right. So we sort of taken the problem and turned it into a linear algebra problem. Now is another time where I will ask you once again, how much of your linear algebra class do you remember? And so I have this question. I wrote in the snakes and ladders problem, but you could equally well, it's the same exact question with, instead of in the snakes and ladders problem, you could put it in the heads problem. And the question is, how many solutions are there to v equals r plus pv? So let's, for concreteness, let's replace snakes and ladders with literally this, what I have written here. So r is 110, p is this thing. How many solutions do you think there are to v equals this plus p times that? And I guess here gamma equals 1 if you want to be a stickler. Okay, I'm going to leave it open. And I gave you the 3 options, infinitely many, 0, or 1. Those are usually the answers. Okay, I will start a timer for 1 minute.
I have a question about the future discount.
Yes, give me your question about the future.
So is there different forms you can give it rather than just a number?
Oh,
Because I'd rather have money now than like 500 years in the future. Like,
yes.
No value.
So as long as your future discounting is time homogeneous, so like if you value 1 year from now is at the same discounting as like 5 years from now to 6 years from now, then it will always be this gamma factor. It's true you could potentially think of a more complicated discounting function. We're not going to do that. you could put it in, right? So you could put in, instead of putting in gamma to the power t, like I put in here, gamma squared, you could put in f of t. This is going to make everything much more complicated. And then in fact your Bellman equation will no longer work exactly. So no. Yes. So yeah, normally people use either a fixed gamma or a gamma equals 1. Yeah. Okay. The thing you could do in that case, you could build the time into your state. So you could have what time it is in your state, and then you could sort of like explicitly build in your weirdo rules about how time works into your rewards, and then it would still fit in this framework. It would just, your process would be much more complicated. Yeah. Great question. Okay, let's give a minute from now. Okay. How many solutions to the equation? 1 more minute. All right, 5 seconds left. Put in your final guesses. Okay, let's take a look. People said 1. 14 people think there's 1 solution. The correct answer is infinitely many solutions. So everybody got wrong. So if you try to solve this equation and you're just like, I'm going to solve it, you're going to have a bad time. There's 1 extra thing you need in this case to sort of nail down the solution. There's infinitely many solutions. Let me, because we did the example at the beginning. I think if you go flip back in your notes and you say like, wait, there was 1 extra thing. So in addition to this equation, which relates them to each other, there is 1 extra thing we need. I'll let you guys think for 1 more minute, and then maybe someone will come up with the answer. What is the extra thing we need? So, oh look, it's already counting down. Good. Let's do 30 seconds. Okay. Okay. Does anyone have a guess as to what is the extra thing you need in addition to the circled equation? Yeah.
You gotta set a value for the final.
You have. That's exactly right. So if you look carefully at what we did, I started out by saying that v of 2 equals 0 in our example earlier. That was like what I did. And if you actually look at this bottom equation, right, the vector v, if you look at the third component, it says the third component equals 0 plus the third component. So like one of these equations says v of 2 equals v of 2. And if you have an equation like v of 2 equals v of 2, it's not useful to help you solve what is v of 2. In fact, there's no information being given about v of 2 at all in here. And the reason that was okay is because we knew it was 0. And we said if you are already flipping 2 coins and you're already there, then you need 0 more coins. You can imagine a world where there's some like casino game where you get to 2 coin flips and they like give you $5 or something. And then v of 2 would be 5. V of 2 can be any value. You still have a consistent equation. So you should think of the Bellman equation tells you how the states kind of depend on each other, but it doesn't tell you what happens at the terminal states. I like to think of this as there's a special kind of reward, a terminal reward, that happens at state 2, and in this situation it was 0. And if you have both of these things together, then you can solve it. So these are kind of like the initial values, or the terminal values. The terminal values of the value function, and they are sort of missing. They are missing in the Bellman equation. You got to insert them in manually, or something. You got to do something. So very good. We're going to see next class lots of different ways to solve it. In particular, we're going to do 2. We're going to do one of them is linear algebra. Like how do you put this in a computer? If you put it in the right way, you can do like matrix inverses, like we talked a little bit about last week. And number 2, there's something called value iteration, which is a nice iterative way to solve it. So that's coming up next week. Don't forget you have a homework assignment due on Monday, coming up in 6 days. So get cracking on that. Okay, see you guys on Thursday.